Okay, hopefully folks are enjoying the music. Checking a few things here before we get started. So far, so good. Thanks, Rihanna. Hey, everybody. We'll give us a few more minutes. So if you can see me in the chat, if you know what I'm wearing, why don't you respond in the chat? Yeah, baby. Star Wars is right. Okay, so as people are joining us, we'll write out a few things that we're going to do today. And we'll make the music go away in a little bit. Yeah, my workout clothes. Let's see here. All right. Hey, good morning. This isn't a costume. This is who I am. Okay, I'm a Jedi today. So let's turn the music off, and let's let's get started. I'm gonna. So if you've got some questions and you want to line them up in the chat, that would be amazing. I am going to start talking about a few items that I got some questions about that I think would be fun for us to discuss as a group. And I'm going to start out first talking about walls in structural systems. Walls are extremely powerful. They are amazing, especially if you know what they're about, how to do them. They can really improve your structure and make it be really, really nice. I'll talk about first with wind, and then I will talk about with earthquakes, and then I will talk a little bit about some weird column layouts and what to do about them and how to deal with them. So again, if you've got some questions, it's time to fill the chat up with questions. I will go back and answer them the best I can. Also, you might want to cut and paste your questions in some kind of document you have on your local computer. So if I don't answer it for some reason, you can just send it again. You're not going to hurt my feelings. So let's start this party out. So let's see here. I think this is the one I want. So let's talk about walls for a second. So my class is doing a project where they are designing buildings, a building, and they get to pick where their wall system goes. And some of them are a little bit nervous. They're like, I don't know where to place it. I'm kind of concerned. That makes sense. I know I was really nervous. I didn't want to mess it up, right? And I get that approach. Now I'm going to start out with a very, very simple structure. Very, very, very simple structure. Just rectangular, straightforward, because you need to understand these before you can understand the more complicated structures. And in this system, let's just say I have my walls over here. I have one wall here, and we'll make it really easy at first. We'll make them symmetrical. We'll do a wall here, and we'll do a wall here, and that's a wall. wall, and let's make those walls the exact same length. So just start out with something pretty straightforward, pretty easy to begin with. So if I have some kind of wind load, and we're going to start out focusing on wind at first. So, and then I will get into earthquake at the end, just a little bit. If I have wind coming in from this direction, wind blowing here, then what I can do is, since these walls break my system in half, and since they are the same length, then I can kind of chop this in half. I can say, okay, I'm going to take half my wind, half my tributary area for my wind, and I'm going to break it in the middle here. Hopefully that was in the middle. Should be in the middle. Well, not quite in the middle, but let's just assume it's in the middle. Halfway between here, I'm going to take this load right here, and I'm going to turn it into a point load. And I'm going to take this load right here, and I'm going to turn it into a point load. And that load is going to find its way through the system. It's going to find its way through the slab, through the other columns, through the beams, through whatever. It's going to distribute. It's going to spread out. It's going to, like, yeah, like here, you need to see this. It's going to go like Jedi magic or something. Yeah, it's going to make that noise too. And it's going to travel through this. It's going to actually look something like this. Well, I don't want to draw it too much, but you can just imagine it kind of like flowing through the system to here. And once it does, we're going to be able to draw and say, you know what, it's going to flow through here. And we're going to draw, for this wall, we're going to draw something like this. And that is going to turn into point loads. Let's just draw one story for now, for fun, just to make it easy. If it's multi-story, it's multi-story. That's what you have to take care of. That's what you have to do. So we're going to make it really simple, really straightforward. Yes, we're going to do this on both sides. And if you're smart and you make your system symmetrical like this, or you make the stiffnesses the same, as in the total length of the wall, the same on both sides, it's going to behave just like this, straightforward, pretty easy. There's a video all about this where I talk about this in lateral load distribution. I just put it out like last week, I think. Now, what happens though if things start to get a little strange, right? That's always what gets interesting in life. So let's say down here I have two walls. Okay, let's say I have two walls down here. A wall here, two walls, and these walls happen to both be the exact same size, or let's not even say what size they are right now. I just say I have two walls. So wall, and let's just say that this one has a moment of inertia we'll call 1, and this one has a moment of inertia called 2. And if you remember how to calculate moment of inertia, it would be 1/12 BH cubed, 1/12 BH cubed. And you would do that for this wall, and you would do that for this wall. And H in this case would be this dimension right here. This would be the H of the wall, and B would be this dimension right here. So if I have my, let's say I want to know how my load is going to be distributed. So let's say this is I1, or this is wall 1, this is wall 2. For wall 1, I would take I1 divided by I1 plus I2. Right? This would be my total stiffness, and this would be my contribution from I1. Now let's say I have 3 walls. Well, I do the same thing 3 different times, 3 different moment of inertia, 3 different walls, same type of system. So this would be this ratio of I1 over I1 plus I2. That would be how much stiffness, or I'm sorry, the ratio of the stiffness, and that would also be the ratio of the load. So let me just draw this in here. So let's say I draw my load coming in here from the side, and this is going to end up being I1 over I1 plus I2, and this one would end up being I2 over I1 plus I2, something like that. That would be how they were distributed. And it doesn't really matter the length. I mean, the length is going to work itself out in this calculation. It's going to work itself out in this distribution, and it's going to work itself out in how these loads are distributed in my actual system. So this, if they were happen to be equal, say they were exactly equal, then this would be 50% of the wall would go here, or of the load would go here, and 50% of the load would go here. The load is distributed by stiffness. The load is distributed by stiffness. That's something you should have learned in structural analysis. That is a key concept for structural engineering, at least in the elastic range. That's true. So that is what the system would look like. That is what the distribution would look like. And I'm looking at my notes here to see if I need to do something different. I think everything is beautiful so far. Now, let's say they weren't the same. Let's say this one was twice as long as this one. Well, that would work itself out in the moment of inertia, and you might end up getting like 70% of the load going here, and maybe 30% of the load going here from that load distribution. Now, what if I have a very odd shaped building, like something, or not very odd wall layout, extremely odd wall layout? Let's say I have something like this. Oh, can't see it, can you? Let's say I have something like this, and now I have only a wall at one side. For whatever reason, I only have a wall over here. Let's just say, I don't know why you do that. Maybe the architect made you, maybe it's the only place you could put it. Who knows? Let's say you have some kind of system like this. And then you have the same problem here. You have the same wind coming here, sweeping down the plane, right, where the waving wheat sure smells sweet. Now, this load has to get distributed to this wall. And so it would, the end for the wall would be the same. It would be, you would take all of this load, every bit of it, and you would put it on this wall, and it would be a point load. It would be, everything would be the same, exactly the same. Same. But there's a little bit of caveat to this. So I'm drawing the wall in the back there. You would take the load from all of this, one big distributed load, and turn it into a point load. And then this would go to the wall, and you would apply it here at the wall. Everything would be the same. But here's the one problem. Here's the one thing that's a little bit different. Is that, do you remember when I talked about that load kind of like, that like spreading, that like Jedi magic that I talked about before of how that load gets here? Well, that's going to still have to happen in this system. So you may have beams in here, you may have columns in here, you may have whatever in here, and that is going to have to, that load is going to have to transfer there. You could almost think of this as like a big cantilever beam. You could think of this as this would be, the wall would be kind of your stiffness, your support, and the body of the building would be like your beam itself. And if you have a cantilever beam that's got a distributed load on it, like this, distributed load, like this, what would you expect to happen in the cantilever beam? Well, it's going to deflect, right? It's going to deflect like that. It's going to have zero rotation there. It's going to look something like this. Well, the same thing is going to happen in your building. The exact same thing. This system is going to deflect. This is going to look a lot like this. This is going to look a lot like that same thing I just drew. And this is going to still be perpendicular in between. And what you have to worry about now is, what is that deflection? What is that? What is it? What is it? And I don't know. And there's not a simple way to do this. This is one of those complex situations where you're going to have to use a finite element program, you know, a pretty decent structural analysis program, 3D structural analysis program, to figure out what that deflection would be. And the simple way to solve it, so you don't have to do that, would be just put a wall over here. I mean, if you could put a wall over here, then all these problems would go away. It doesn't even have to be exactly the same size of wall. Okay, you can still distribute that load by stiffness that way. So this is where, this situation where you have high amounts of stiffness on one side, and you expect the load path, that's a very important term, load path. You have to, because the load path would have to go through the building, it's going to cause some kind of massive deflection. That has to be checked. Not only does it have to be checked because you're worried about it hitting something else, but you have to be checked because you have cladding. What's cladding? That's the brick, that's the windows, that's the stone, that's the whatever. You're going to ask that cladding to do a lot of movement. And is it going to fit? Is it going to work? Is it going to do what it's going to do? And you might say, well, how do I know? Well, you would find out what your deflection system, what your deflections were, and usually you would talk to the cladding expert. That's usually someone that's selling you the cladding, or is as a subcontractor that designs a lot of those, and you'll reach out to those to ask them questions about, hey, what do you think about this system? What do you think about this amount of deflection? And that's one reason why people don't do stuff like this. There's too many logistics. So it's much easier to put another wall over here, and then you don't have that. You can find a place for the wall in your elevator cores, in your stairwells. There's lots of places to put your friends the wall. Now let's move on to how earthquakes work with walls, just for fun. You're not designing earthquakes for my class or buildings with earthquakes, but you may run into structures that have earthquakes in them in your life, or you may be a visitor on the outside. And thank you for coming here, visitors. I really appreciate you. We've had a lot of fun with your questions, and I'm looking forward to getting more questions from you today. But if you have a system like this, structural system, we'll go back to our same rectangular building. So simple, easy, whatever building. Now, what you have to watch out for is that sometimes, let's say I put my one wall here, okay, and let's say for whatever reason, let's see, what's the best way to do this? Let's say I have to have another wall here. Let's just say, for whatever reason, that's the layout. That worked out. That's where it ended up being. So here's my building. Here's my walls. Now, what you have to do is you have to calculate something called, you have to calculate two values when it comes to earthquakes. You have to calculate one thing called the center of mass. And then you have to calculate something called the center of stiffness. Now, the reason you have to do this is that the earthquake acts on the mass of the building. When the earthquake starts to shake and it starts to move around, what starts to move is the mass. Well, in a building like this, you would say, where is like the centroid, basically? Where is the centroid at? And it would be like here. This is where the centroid is at. Here. You could imagine drawing a line from here to here and a line from here to here. And that is where the center of the building, the center of mass of the building. So this is what's going to get moved back and forth as the earthquake goes in this direction. Or if the earthquake goes in this direction, this is what's going to get moved. But let's just talk about this direction first. And then we have something called the center of stiffness. And what the center of stiffness is you'd say, what can resist? What can resist? Where is my resistance point? Well, it would be halfway in between these walls. Maybe I might draw it to be here. It would be halfway in this dimension between the walls, halfway in this dimension between the walls. So we'll call this one the center of mass, CM, and we'll call this one the center of stiffness, CS. Now, what that means is that this is what's going to want to move, and this is what's going to want to resist it. And because of that, because there is a difference between those, a difference in dimension, a difference in dimension in this direction, and a difference in dimension in this direction, it's going to cause a torsion. It's going to cause a torque. As the earthquake starts to happen, if you lay it out like this building is going to start to twist back and forth. And that's going to put different moments on the building. It's going to cause different amounts of moments for all of your walls. I mean, you'll have walls in this direction, but you'll also have walls going in this direction as well. And this twist, this difference, this torque is going to cause, again, different amounts of loads. And they're going to depend on the stiffness of the wall and also the distance from the center of mass, or actually, I think it's actually the difference from the center of stiffness is actually how you you determine those. There's a whole lot of stuff that goes into that. I had to learn all this for my PE test. I had my PE in California, and California is all about earthquakes, and so there's several of these on my PE exam. There's a seismic specific exam for the state of California. Not very fun, but made it through. So hurrah! So that's kind of how that works in when it comes to earthquakes, when it comes to these wall systems. Now I'm going to bring up one more topic really quick, and I think most people probably get this and probably understand this, but I just want to make it abundantly clear. So I'm gonna talk about it. So if I go back to my same box system here that I've been talking about. There, so you can see it now. Pop my little projector. I will pop it back. It's back. So if I have a wall, that's here, and if I have a wall that's here, and if I have a wall that's here, and my wind starts sweeping down the plane and blowing here and blowing here, how much load goes to that wall? Well, none. Well, that's not totally true. A very, 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 very small amount. And how much load goes to that wall? Well, if these two are the same length, half of the load would, and half of the load would go here. But you'd say, like, what? This is a wall. I thought load is distributed to the walls when you have a lateral load, when you use walls and lateral load resisting systems. Yeah, that's true. But any wall that you have that is perpendicular to where the load's going in, it doesn't do anything because the stiffness is so small. Think about how to calculate the stiffness for this wall. It's like 1/12 BH cubed. And then you have this wall, which is, you can use the same 1/12 BH cubed, but the H's are totally different. The H in this case is here, and the H in this case is here. This H may be 12 inches. This H may be like 20 feet or something like that. They're totally different. They're not even remotely comparable to one another. And so because of that, we ignore this. We ignore it. And we assume all the load goes here. And I got a comment over the weekend that was pretty interesting in some of my videos. They told me, Tyler, it was about my Jedi video. They said, you are bad at math. Bad at math. Well, yeah, well, they're being exact. They're saying if you exactly calculate how the load's distributed, then there will be some load that goes here. So you're bad at math because you're leaving things out. That's what you do when in math. When you leave things out, you're bad. You mess it up. But I told them bad at math can equal good engineering. Well, we'll just say I wrote engineering there. Can't even spell engineering. Well, don't have enough space to finish it. So there you go. I'll put the G on the end. Bad at math equals good at engineering. Because I don't need to spend my time. The most valuable thing that I have is my time. I don't need to spend my time finding this answer exactly when I can find the essence, the best estimate, the get myself done so I can go watch more Netflix type thing. Yeah, that's what you want to do when you are an engineer. You don't have to worry about getting the math exact. Now, I don't mean making horrible, sloppy errors. That's not what I'm talking about. I'm talking about if you're intelligent, you can realize when you can do bad math, but yet be a good engineer. So one more question that some folks had, and I hope the chat's filling up. I see more chat things coming in on the side, which is super exciting. One more question that I had was on frames. So I'm going to go back to my box that I've been drawing all day long. Box. And again, if you have more questions, this is a great time for you to fill up the chat on the side. I really appreciate you being here. It's been a lot of fun for me. If I have a structural system that looks something like this, let's say I'm going to draw two different structural systems. One that's very straightforward, columns that look something like this. And then one that we'll draw it down here that is looking normal, and then all of a sudden, for some reason, my columns are offset. You might say, like, what? Why would that happen? Usually because there's some kind of architectural treatment or some kind of special thing the owner wants that allows you to not put all your columns in the places that you'd like them to. That happens. So if we were doing this same thing I told you about before, where we have our lateral loads coming in here and our lateral loads coming in here. Now I didn't draw all my columns in, but what I would do here is I would find my tributary area for this system. Let's say it's here, and I would find my resultant load. Let's say it's here, and I would put it on that structural system over there. I would put it on this boom, 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 schmack, right? I put the load right there. That's what would happen for this one. Now, the question was, though, how do you handle this one? What do you do here? This made sense. Everything's in a line. What do you do here? Well, there's a couple ways to do it. One way to do it is that you could put this in 3D in a program, and you could you could load it up just like you would here. You could put the whole thing in 3D, and so let's say, I'm going to try to draw it in 3D. Column, 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 and then these columns kind of split. There's a column in the back, column in the front, column in the back, column in the front. And the beams would go like this, and the beam may go like this, this, this. 3D, baby. 3D. And then you put the load on it like this, and you would see how the load is distributed. Now, I think that's what a lot of people would do. I think that's what a lot of people, they wouldn't want to think about it. They wouldn't want to get to it. They wouldn't want to deal with it. So they would just do something like that. And that's fine. There's nothing wrong with that. But there's still a way to make this into a 2D problem. And there's a couple ways. One way is to ignore these columns over here. Ignore them. Yeah, you could ignore them if you wanted to. And you could just make your structure be these 3 columns right here. There's actually nothing wrong with that. There's I would say 90% of the time, there's nothing wrong with ignoring stiffness because it's still there. It's still going to help you. You're just assuming it's not there. You're like assuming that there are no columns over here. And instead of being like whatever 5 columns, 1, 2, 3, 4, 5, I only drew 4, should have drawn 5 in here. Instead of having 5 columns, I could just do it as 3 columns. 3 columns. 3, 3, 3 columns. And there's actually nothing wrong with that. 0 wrong. Nothing wrong with that. And you could put the load on it and you could solve it and everything would be great. And I would probably go ahead and use the same size columns and the same size layout over here. There's nothing wrong with that. You can do it that way. Another way to do it, though, would be to take these structural systems, these systems, and maybe even split their stiffness up, as in take half the stiffness from these and half the stiffness from these. Again, I'm assuming this happens over here as well, but or some part of their stiffness. Maybe it's not half, maybe it's some part of their stiffness, and make my own columns, like my own columns. So when it comes down here, I would use this column would be here, this column would be here, this column would be here, and I could take some of the stiffness from these columns, some of the stiffness from these columns, and I'm going to make my own like pseudo column here. So if everything's laid out evenly, this makes it easy. I could take half the stiffness and put it here, half the stiffness and put it here. What do you mean by half the stiffness? Well, I could just assume that if this is let's just say this bad boy is a 12-inch by 12-inch column. And let's say that this bad boy is just make the math a little bit easier. We'll say 14 by 14-inch column, whatever. 12 by 12, 14 by 14. I could take half of this depth. The depth is what matters, which is 6, and half of this depth, which is 7. And I can make myself my own column here that would have a dimension of 13 inches by 13 inches, and I can rock and roll with that in that structural system. That's doable. There's nothing wrong with that. You just have to have a logic. You have to have a reason. And that logic can't be totally crazy. It has to like be believable by other people. And this is one reason why you want to write out really good notes in your design calculations. I don't care if you do everything in the computer. I don't care. I don't care if you type it. I don't care whatever you do. You have to leave very, very good notes to people that are going to come after, people that will check, the people that may inherit your building in the future. You know, they have to do whatever they have to do to it. They have to retrofit it. They have to modify it. They have to whatever. You need to have that packet of calculations out there so that people in the future can understand what it is you're doing and how you're doing it and why you're doing it and what that's all about. Oh, my robes are opening. Let me fix those right there. So you have that's your responsibility. And whatever you choose here is fine. You can choose any one of these solutions. You just have to tell them what you did and why. All right. So this is chat time. So we're going to see what we got. Let's see. Khalid wants to know, could I explain analysis of beam sections? So I've got videos on that, Khalid. If you've got specific on beam sections that you want to hear about, this would be a great time for you to give me specifics. But I've got several videos on shear, on moment, on designing, on doing all kinds of awesome stuff with beams. And so if you could be more specific about what you want to hear about, I could try to answer. Let's see. Lou Alcindor says, are carbon captured cements as strong as normal cements? Do they have the same durability? So, Lou, I don't know. I think that is a great question, and I don't know anyone that knows that. I know that people that sell carbon captured cements will say that they're great and say that there's improvement in strength. But I don't think anyone knows about durability of those materials because they haven't been around that long. I mean, do you know that modern concrete, stuff we use today has been around for about 120 years? Man, a little bit longer than that. Joseph Smearton Lighthouse, you should check it out. That's the rebirth of modern concrete. That's about 120, 130 years old. That's it. So we have no idea how this carbon captured stuff that's been around for maybe 4, 5-ish years, we have no idea. And I don't think there's a lot of research that's been done on the long-term durability that I know of. Maybe it exists. If it does, email it to me. I'd love to learn about it. I'd love to hear about it because it's a question that I have as well. Let's see. Okay, so Kyle wants to know, to find the appropriate length, he's talking about a wall. To find the appropriate length of a wall, should we be multiplying by some magical number or magical something like that? So Kyle, the short answer is no. Positively no. That's not what you should do. What you're going to do in systems like this, there is no magical stiffness. Let me change this jigger here. Boom. In these systems like this, what you're going to do is you're going to see how much wall does my architect, does my owner, does my building layout allow me to use? And you are going to use that the best you possibly can. And if you need more, you will ask for that. And you'd say, well, how do I know if it's enough? How do I know? Well, you have to calculate the capacity of the wall and you have to see what the stresses are. And don't worry, I am going to teach you how to do that. There's a video upcoming, but first we have to get through columns because believe it or not, walls are big columns. That's what they are. And if you understand how to design a column, then you will understand how to design a wall. It's just a small tweak. And so, well, not small, but it's just a tweak on a wall. So what you do in a wall section is typically you will know for certain areas of the country, whether you're dealing with wind, whether you're dealing with seismic, from your past designs, you will know about what length of wall you need to be satisfactory. And what you're going to find is that the answer most of the time, a ballpark number is something around 20 feet-ish. Right? If you can get about 20 feet-ish in most moderate sized buildings, moderate office size buildings, if you can get 20 feet of wall, then you are usually pretty solid. Okay, usually pretty solid. And that's not true as things get really, really, really wide in this direction, or if things start to get really, really high. And you'd say, well, okay, well, what do I do then? Kyle, I wish I had a great answer for you, and I don't. And what you're going to have to do is you're going to have to find out what works and what doesn't. If you've noticed through my videos and in our class, sometimes I have known the way through the maze and I've showed you that way. I've said, hey, go this direction. This is going to help you. This is going to save you time. There's some times in your life where you're going to work on things that no one else does. You're going to do something unique that no one else does. And in those cases, you are going to have to figure your own way through the maze. My own way through the maze? How am I going to do that? Well, that's why we give you this project and things like this. That's why you ask great questions. And if you can't find someone that can give you the way through the maze, or even if they give you the way, you need to check that way. You need to stress test it to make sure it's right, to make sure it works for your cases and for what you're wanting to do, because sometimes it may not. It may work for them, but it may not work for you. Now, when it comes to these friends of the walls, if this is something you really want to learn out, there's not some magical number about what it needs to be. Your length of your wall needs to be way larger, or the moment of inertia of your wall needs to be way larger than the moment of inertia of all your other systems put together, all these columns and other things like that. And I showed you in the video how to calculate that. It's pretty easy. You use 1/12 BH cubed, and you do that for the wall. And you use 1/12 BH cubed, and you do that for every other lateral load resisting system in here, basically the columns. And you total those up and you compare them, and you'd say, what am I comfortable with? What am I comfortable with? Well, I'll tell you what, if my wall was 10 times stiffer, my wall systems were 10 times stiffer than all of my other structural column systems, that means they take 90% of the load, theoretically, and the columns would take 10% of the load, then I'm fine as a structural engineer, assuming that the load is going to take all the load. Because to me, 90% is very, very, very close to 100%. It's kind of like what I said before. Bad math equals good engineering. Like I said, is 90% 100%? No, it's not. It's not. It's not. But to me, it's close enough. So when is it not close enough? Well, you need to make that decision for yourself. And when it gets things like 75% to the wall, 25% to the columns, that's when I start thinking like, okay, we need to make sure this column system, or I'm going to be looking for ways to make my wall longer. That's what I'm going to do. All right. Hey, thank you. You must like Jedi robes. Thank you. I really appreciate that. That's so kind of you to say. Oh, man, we got another one in here. Hey, thanks so much. I really appreciate you tuning in. Let's see. So Lewis asked an interesting question. Lewis, thank you for asking the great questions last week, and thanks for coming back with questions this week. Lewis said, do you think the problem with Citicorp Tower, and I have a video about that, and you should check it out. It's one of my most popular videos, was related to the stiffness arrangement of the columns, or was it only because of the area exposure to wind loads? It was both. So I had actually content that explained this, and I should probably make a follow-up video about this, in all honesty, Lewis. So thank you for asking this question. So we'll answer this really quickly, and we'll try to get back to the other folks. So in the Citicorp Center, what originally happened, and I'll try to make this pretty quick, is, and this would be a great lead in if I do make a video about this. What the Citicorp Center is, it's a very, very tall building in downtown Manhattan, massive, massive building. And what they were using a skyscraper, and they were putting their columns in the corners, and they were going to be super columns. They also had an elevator core in the middle, okay, that went something like this. So it's very timely, very ties into exactly what we're talking about with wind loads. So the wind loads were coming from this direction, and the wind loads were coming from this direction. And in systems like this, boxes and like this. They work great. Everything is good. They're stiff. Everything is wonderful. And what they found out is after the architects had done this design, that at one of the corners, there was a church that was there. And that church didn't want to move. They'd been there a long time, and they positively did not want to move. And so what the engineers did is they said, I'm going to take these columns and I'm going to move them. I'm going to move them here. 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 And I'm going to leave my elevator core in the exact same spot. So I'll draw the new building over here. It's going to look a lot like the old building, a lot of the same dimensions, but now it's going to have these bad boys here, 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 and then elevator core in the center. Now, in this case, what the engineer did is they said, I needed to move these. No big deal. I'm still going to put my same winds on them. No big deal. And they did this. They did the analysis like this. They did everything like this, and everything they said was fine. It was going to work out. But one thing that they didn't check in this type system, if I have what's called a quartering wind, so this would be a little bit strange, but this is a wind that comes at a diagonal. Right? This is a wind that comes from, so if I come from this dimension back, and if I come from this dimension back, this would be a wind that comes from here, a quartering wind. If I have something that is like this quartering wind is taken by this column. As in, it's still, this column seems more stressed, because if we think of where the center of stiffness is, the center of stiffness is here, but you're still going to, and you would have more load on this system, but this column is closer. This column is closer, so it's further away. It's more stable. You get more benefit because the eccentricity is larger. The leverage is better because that column is further away from that center of stiffness. But now if I put my same quartering wind over here, my same quartering wind where it comes out like this, same quartering wind, same thing, everything's the same. And the load comes here, and my load comes here. Now my center of stiffness is here, here in my system. And now my columns are not near as far. The leverage that these columns have is much, much, much smaller. And I calculated it. I have notes on this. I've had calculations like this. I didn't put it in that previous video because, like, I don't know if people would like it or want to learn about it. So I probably should make a follow-up video where I explain it even more. But this quartering wind, now that there's this column that further away, now these loads are actually go way up in this system. Like, they go way up because you're just much closer. Your feet are much closer to this center of stiffness here in the center, and because of that, the bracing in this system was overloaded. And they actually thought originally that it was going to all be in compression. The entire system was going to be in compression because the loads above it coming in and out of the page were going to be so high that they were going to keep this in compression and keep the diagonals in compression, the lateral load resisting system. And that no longer was the case. When you do something like this, you get more uplift. You get more tension here. And because there was more tension, then those things that they thought were going to be pure compression, I've even got drawings of the details, or some drawings of the details. They originally made and they were steel connections. They made them look like this. They had a bolt. They had a plate on the opposite side that looked like this. They had a column that looked like this, and they had bolts. So they had bolts over here, and they had a bolt in the system. And originally it was all in compression, but now once this happened, these went into tension, and they didn't figure it out. Here's the crazy part. They didn't figure this out until the building was already done. Like, the building was already constructed and finished. And how they figured it out is that there was an undergraduate student that was doing a report on the building. And during that work, she figured this out. She actually did the calculations herself and figured out that it didn't work, that something wasn't right. She had all the calculations. She had all the layouts for the building. She figured out that it didn't work. So she alerted them and she asked some questions. And actually they assured her at the time that there was no problems and there was nothing nothing to worry about. And then there was, and they figured it out. And it's a very cool story. You should watch the video, and you should also watch the interview. The student found me. Okay, she contacted me, and she said, I watched your video. I think it's really cool, but I'm the student from the video. And she gave me her papers that she worked on, her story checked out. It was unbelievable what she did. It's a really cool story, and you should watch the video if you haven't seen it. So let's keep moving. Let's see. Yes. So Arnold asked a two-part question. He says, if we have shear walls in a building, like we've been talking about before, shear walls in a building, instead of taking the tributary area between each column, that's right, we don't look at each column, we look at the tributary area for the wall, right? So cut the building in half. This would be half the tributary area for the walls. This would be half the tributary area for these walls. And all of that load, instead of going on columns, it just goes to the wall. There's a video about that, lateral loads. If you haven't seen it, check it out. There you go. And we don't put it on the frames. That's right. We only put that point load on the wall. That's exactly right. That's what this is talking about. If you haven't seen the video, you should check that video out. Okay, so here's a question. It was, why design a system as continuous beams instead of simply supported beams? So that's a good question. So one could say, so let's just say, I believe what the question is, and if it's wrong, then you can let me know. If I have a system like this, and I actually draw it like this, and I have some kind of load that's on it, we'll just say it's a distributed load for fun. This gentleman is saying, why am I designing it like this? Why not break it up into a series of simply supported beams that have the exact same dimensions? These would be the same. This would be the same. This would be the same. The loads would be the same. Why not do this? And if you do this and you find the moment on this, it would be WL squared over 8. Yeah, it looks like a parabola, and it's WL squared over 8. And if you do it on some system like this, it will be less than WL squared over 8. And it will look more like a bunch of continuous beams. It would look like, it's going to look something like this. Something like that. And these moments, these maximum moments, these maximum positive moments will be less. These things will be less than WL squared over 8. And you might say, like, so what? So why not just do this conservative one? Well, then you could say, well, that's true. That would work for the positive moment, but then what would you use for the negative moment down here? Well, you could, if you wanted to. This is totally legit. Again, this goes back in the same mindset of bad math equals good engineering. And what you could do is you could actually use WL squared over 8 for this negative moment as well. You could use it for the positive moment. You could use it for the negative moment, and you would be conservative. You would be conservative, and it would work, and it would be fine, and there'd be nothing wrong. And that is legit. That is a fine way to solve that problem. That is a very conservative way to solve the problem, though. Extremely conservative way to solve the problem. And in the modern age of structural analysis software, that is not very hard to use and pretty straightforward if you put a little bit of time into it. You can put this in pretty quickly, put some loads on it, and get a better estimate than just WL squared over 8 here and WL squared over 8 here. And when you have that better estimate, then that will help you get a more exact and save your client money. Now, this isn't always sometimes worth it. Sometimes you do something very, very conservative like this, and that's fine. This is a fine way to check what your loads would be. And this is a great, cool back of the envelope approach. But when it comes down to really designing, most people, in my experience, don't use something like this. They'll spend a little bit of time to put something like this in a computer program and figure out what those moments and shears are and better tune their design. And if you watch the video that I posted yesterday on how to design like a Jedi, hence I got my Jedi robes out, I tell you some really sweet tricks on how to design this once you know the positive and negative moments for your structure. Let's see here. Let's see here. This says lectures in my steel design of your playlist do not cover design of compression members. We can get lectures on design compression members in steel, and we have lectures on reliability levels. Oh no, there are tons of videos about design of compression members on my steel notes that are posted online. It's all about buckling, right? Steel doesn't fail in compression, as in crush. Steel buckles in compression, and there are tons on there, and you should check it out. Now, reliability is not my thing. There's Dr. Solomon, who's at Oklahoma State University. He is a guru in reliability, in steel reliability. Check him out if you want to learn more about reliability of steel structures. But there are tons of videos about steel failing in compression in my on my notes. Some really, really cool ones. Awesome. This is a great question. Is there a minimum thickness for shear walls that needs boundary elements? We've got in Columbia structural systems that have really big problems. So this is a great question. Now, and I'm not going to probably give you the most satisfactory answer. I'm going to give you a stepped answer on this. I don't know your problem. I don't know your situation. I don't know what you're doing. And so it is very dangerous for me to make comments about exactly about what you're up to. So I'm going to make some general comments that they'll help most structural engineers, and I hope it can help you as well. But I have to be very, very careful here, not taking what I'm saying here as exactly applying to your situation, because it may not. But you asked about what is the minimum thickness of a wall. So almost always when it comes to a wall, you're not going to want to go below around about 300 millimeters or so. Is that right? No, let's see here. Let me just do my English units. You're never going to want to go less than 12 inches in a wall, ever. And that would be 250, another 50. Yeah, it's about 300 millimeters, I believe. I did the conversion quickly. You're never going to want to go below that. That's just the absolute positive minimum that for a major structural wall, without doing some serious calculations and some serious figuring on an actual structure. And that's for a major like commercial building. Now, if you were going to do like a residential building, then you could probably go less than this. And that's something that then you could check out and see what actually fits for you. Actually do some more calculations. Now, another thing that almost always common controls when it comes to a wall is anchorage, is development length. So if I have a beam or something else, a beam that's framing into this wall that's coming in this direction, I have to have my bars come into that wall, and actually I'm going to hook them down. So if my eye was here on the side, then what I would see would be a beam coming in a beam coming in. Here's my wall. Here's my wall. Here's my wall. And then I've got my stuff coming in and actually anchoring into the wall. Believe it or not, this hook dimension often will control the thickness of your wall. Often. And actually it'll control your thickness of your columns a lot as well in a lot of structures that I've designed in the past. May not be true for you, but it's what I've seen. Now, if you use something like a headed bar, and they're not as common, but in seismic areas they're becoming more and more common. Let me adjust something here. Let me adjust the force a little bit here. There we go. Hopefully that'll work out for us. Yeah, dangerous to play with the force. Yeah, didn't quite work. Move it here. There you go. I'll just go like this. Sorry for the color change. If you have something like this, almost always controls the thickness that you would use for your columns and your walls. Yeah. So I mean, as far as putting that wall in, I guess if you're adding this wall and you don't have something like this, then your calculations are going to help you figure out this, and the thickness doesn't matter as much because it looks like you're retrofitting. From what I can see, you're trying to retrofit in something. Oh, that doesn't look good. Yeah, that's just kind of where it's at. Let me move this here. All right, that's better. Let's keep moving. I hope I answered your question. If I didn't, then please ask me more. I'm getting almost the end of my chat, so send me some. Hey, thank you guys. Love you guys so much. Let's see. Oh, here we go. Explain the best practices of anchoring bars and development links in joint column interface of continuous beams. Great question. Hard question. And if you've not had strut and tie modeling, if you do not know what strut and tie modeling is, I talked about it in my last live cast a smidge. If you don't know what that is, then you need to learn it. It's very, very, very powerful. Now, so let's just talk about, and I'm not going to give you a full answer. I'm sorry. I'm going to take like 20 minutes to truly give you a full answer to this question. I probably should make a video about it. It's kind of complicated though. So I'm going to just I'm going to try to do a gloss over here. So if I have a structural system, a set of continuous beams here, and I'm just going to draw a part of that. And I will draw, and we'll start talking about the interior joint first. And I have a video I just published yesterday about some of these topics. But when it comes to your reinforcing steel, you need to anchor it well at your outside column, and then you're going to need to extend it. You need to have at least 2 bars go the entire length. So these bars have to go the entire length. You're gonna have to lap those bars at some point. I would try to take them past the first bay and lap them here, but it just depends on what your bays are and where you can. I might try to lap them instead at not where the moment is the maximum, but where the moment is the minimum, about the third point or about the quarter point in this span. That if I had to do a lap, that means if I have to do some kind of cross between my bars. Anyway, I'm going to extend these bars wherever they need to go, and I'm going to have bottom bars as well. So these bottom bars are going to go here. They're going to extend all the way through the joint as well here. This is the joint. This is what the question's all about. How do you do the steel layout in the joint? And now I have to have column bars. And we haven't talked about columns yet in this class, but there will be column videos coming out. I'm shooting them now. And so my column steel is going to look something like this. Now, I'm going to have stirrups. Those are the shear stirrups that I use to design for these. They're going to look like this. And then I'm going to have stirrups that go here. And then I'm going to have stirrups on my columns as well. They're going to do the same thing. I'm going to have stirrups that go here. Now, when it comes to this system, you're pretty much good to go. And you can use something like strut and tie modeling. I'll write that out. Strut and tie modeling. It's developed in Switzerland in the 1970s. Very, 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 very powerful. And I've got papers on it. You can find my papers on it. You can find other people's papers on it. It's in the ACI design code. I don't love the way that they treat it. I think they're missing some of the philosophy behind it. But you can use a strut and tie model to check these for your moments. And my experience is these work really, really well and don't have problems in interior structures for most strut and tie models, because the dimensions and steel layout that you need and the interior columns are usually not a problem. Now, what gets more concerning is when you have a system like this. So we'll put our same steel in. We're going to have our anchorage over here. We're going to have our column steel come down here. Our column steel come down here. And then we're going to put our stirrups in here and put our stirrups in here. And most of the time, you do not include stirrups in the joint. Most of the time, you do not include stirrups in the joint. If you're worried about that, and then you can do something called a strut and tie model again. And then what a strut and tie model is going to do in this case is it's going to, I need to pick a different color. I'm sorry, this is going to get a little bit nuts. But what you're going to do is you're going to look and see if I have tension up here, I'm going to have compression down here. So my strut is going to look something like this, and my tie is going to be something like this. And you're going to see, is that system going to survive? Is this truss that I envision in my head, is it going to have the capacity it needs to survive this type of system and these type of loads? And most of the time, the answer is yes. Most of the time. Sometimes in seismic, it's not. And actually, the biggest, but then you can get reversal of loads. So this doesn't have to be in tension at the top. Sometimes this can be tension at the bottom. And in that case, your strut is going to have to look like this. So the first strut I drew would go away. It's not there. You'd have a strut that would appear in this direction, and you would have a tie down here. Now, sometimes this is where you can start to have an issue. Now, if this was in compression and you don't have a way to transfer load here, that's something where you might need to add an extra stirrup. You might need an extra stirrup right here. You might need to extend that bar all the way. You might need to extend it and hook it. You might need to extend it and put a head on it. There's a lot of different ways, and this is the problem. These are the details. These are the issues that you can discover when you truly understand strut and tie modeling and you think about all the different load cases that can be applied to a structural system. All right, let's keep moving. Yep, here's a good question. How do load-bearing structures resist lateral loads? I think if you just check the overturning, is that enough? How can I design its beams? So the question is that if I have a gravity load system, so if I have a wall or whatever structural system that is so heavy, there's so much dead load coming down, that when I put my wind on it from the side, usually my wind loads look something like this, except our project, which I just made them uniform. You're welcome. If this load is high enough, if the dead load is high enough, then there'll be so much compression that this won't have any uplift. So you have to remember that there is one load case you have to check for this. This is 0.9 dead load plus like 1 wind load. I believe that's what it is. I'm just doing it off the top of my head. You have to make sure that if only, at least in ACI, you only use 90% of the dead load plus the wind load. But what you can, if this is still true, that when this wind comes blowing, then you don't have any uplift, like no uplift right here, like zero, like none, like nothing, no uplift, doesn't go into tension. Then if that's true, then you can be okay. Now my bar has gone down to red here on my internet, so that means I hope it's not horrible. And anyway, in this case, you don't have to actually even design your lateral load system. You can just use for for this. You can just use gravity loads and you'll be fine. So let me check on something just a second. Okay, I had to check. I don't know why my internet is low, but it's low and hopefully it will get better soon. Hey, thank you so much. Let's see. This one says, while designing shear walls or bracing to resist lateral loads, why don't we just use dimensions of the wall? You can, but that doesn't always help. You can't always do that sometimes. Sometimes people, architects, buildings, whatever, they don't allow you to do that. And these last two questions here, at least the last two questions that I've seen, and if you guys have any more, I'll do my best to answer them. And if not, then I understand. Let's see, what methods do I prefer to find the values of the real in the center? For those, I usually use something like summation, just same things I showed you before is what I end up using for the approximate center of stiffness. So I usually use, and this isn't something I do a lot of, so you may have a better answer out there than I do, but I just use something like the summation of I of all elements. You asked for center of stiffness, pardon me. So you would do something like a centroid calculation, only you do it with stiffness. So you would look at the stiffness of the member times the distance from the center of stiffness. You would sum all of those in the, it'd be the summation in the denominator, and in the numerator, it would be that for that member. And I would use something like that to find the center of stiffness, kind of like what I showed before. Let's see. Let's see, this is the last question I have that's showing here. Need to be retrofitted with stiffening trusses after Tacoma Narrows collapsed in the 40s. The Bronx Wheatstone required this. Yeah, that's true. They did. A lot of suspension bridges did require retrofitting because of that. And it was because they made them very, very slender. They made those deck trusses very slender. And I don't see more questions. So after this one, if this is the last question I have, then I am going to end this sucker up. But what happened on the Tacoma Narrows Bridge is they made the system very, very slender. They made the deck system extremely slender, and as it would, this is the suspenders here, and so as it would deflect, as the wind would start to blow and come from this direction, the system would start to deflect. And once it did, it would start to act like a wing on an airplane, and it would actually catch the load. And so when that would happen, that would make it, then it would start racking in the other direction, and it would catch it in that direction as well. And it would do this over and over and over and over again, keep catching the load, and it would be like a swing almost. You know, when you have a swing, like if you're pushing a child in a swing or something like that, you have a person, you know, whatever, this is going to be a poorly drawn swing, I'm afraid, but here's a swing. And, you know, if you have like person sitting in swing, right? And you're going to push them as that person goes back and forth, you push them every time. You push, again, push, and they go higher and higher and higher. Well, the same thing happened here. The exact same thing happened here. The wind would start to blow a little bit. It would move just a little bit, and it would get pushed. and then it would go back, and the wind, and then it would tilt back, and it would get pushed, and then again and again and again and again and over and over and over and over and over again and again and again, and then it fell off. It fell apart. It shook itself apart, and it actually collapsed. And the way to fix that was to actually add a deck stiffening truss. So they came inside here and they put a truss. They actually added a truss to the bridge. So this is what the old bridge used to look like, something like this. Bridge. This is that very slender, beautiful, amazing deck. And this is the suspenders. Suspenders. Those are the things that hold it in place. Then what they did is they came back with a structural, with a truss. They made it really, really stiff. And when they made it really, really stiff, this initial deflection, this initial perturbation, this initial movement couldn't happen. It didn't happen. They decreased that initial whatever. Kind of, you can think of it as if the person never starts swinging, if the person never kicks off backwards when they swing, the little child or whatever, or me, I like to swing. It's fun. If I don't kick off backwards to start swinging, if I never get it started, then the pushes that a person behind you would give you will never happen. The pushes that the wind is going to give you will never happen. So that's the Tacoma Narrows Bridge, and that's why they need to add that structural system. I should probably make a video about that as well. All right, I'm running out of questions here. Yep, and Lou's right that the George Washington Bridge, which is a very over-designed bridge, but that's right. But the gravity loads, they were so heavy, didn't have the same thickness problem. The same, it wasn't as thin. It was much stiffer on its own. And you're right, George Washington Bridge did not require a deck stiffening truss. That's exactly right. Hey, thank you for the nice comments. I appreciate it. And here we go. Let's see. Hey, when do I go live next time? In 1 week. I go live every Monday to the public. So there you go. You should attend. Yep, and you are right. The George Washington Bridge is a double-decker bridge. That's right. And it sounds like you know a lot about George Washington Bridge. If you do, reach out. That'd be fun to learn more. I'm always interested. Would a precast system of beams? Let's see. So the question is, and this will be, I'm going to answer 2 more questions. I'm going to answer this one and one more. Thank you so much for attending. Thank you so much for being here. This has been a ton of fun. I really enjoyed doing this, and I did it in my Jedi robes. I dressed up. Maybe I'll pick a different outfit for next time. And if there's more topics you want to hear about, or then let me know. I would love to cook them up for you. And so the question is, would a precast systems of beams supported on precast columns be considered simply supported? That's a great question. So what they're talking about is that if I have a column and they're discrete, they're precast, they're not hooked together, and then I take a beam and I place it, and another beam and I place it, and would I consider that continuous, or would I consider that simply supported? Now, what you have to do is you have to think about, in a system like this, how is the load going to travel or transfer? And if I zoomed in on this connection, one of these connections where I have, let's say I have a column here, and let's just say I have a bearing pad, because most of these are built with bearing pads of some sort. Let's say I have a bearing pad, and let's say I come back in. I know a lot about precast. I've done a ton of precast in my career. I know there's people out there that have done more, but I've done quite a bit. If I have a structural system, you can't see it, can you? Apologize. Let me make myself small. Pardon me. Whoop. If I have a system that looks something like this, um, then, and this is my beam and this is my column, this is this connection here, then yeah, that is simply supported because there's no bending, there's no moment that's going to be transferred there at all, like none. But most of the time, but let's just say that we added more concrete to this. Let's just say we added like a deck on top of it. Um, and now I'm going to draw my detail here in the center. So let's say I have my column, and now we have a beam comes on one side, or bearing pads on both sides. And now we have a beam that comes here, a beam, a beam, a beam, a beam, a beam, a beam, something like this. So again, that system again is going to be simply supported. That would be something you would design to be like this, because there's no moment transfer there, like none. Now and this is common in bridges. If I'm in a seismic zone, then what I might do is I might actually add steel to this. I might actually have steel in the top. I might put steel up here, right? And I might have steel actually that comes out of the column that tries to tie these together. And I might encapsulate all of this in concrete. Everything's encapsulated in concrete. If I have provided a load path, if I have designed an adequate load path to transfer my tension and compression here from my beam to my column, then I can design this as a fixed connection. But I have to make sure that there's a load path there. And my favorite thing to use is strut and tie modeling to check my load path and make sure that it's satisfactory. But then there are places like in Texas, and I practiced in Texas for a while. They do something that's a little bit different that they call poor boy continuous, right? Yeah, poor boy means it's not quite continuous and it's not quite simply supported. It's somewhere in the middle. So if I have a beam like this, I have a beam like this, and I do something like a topping slab on top of it. So let's say I tie reinforcing steel up here, and I put a topping slab on top of the whole thing, cast just a topping slab up here. I don't necessarily encapsulate all these. My slab's just up here at the top. Okay, that's what they call a poor boy continuous. And I didn't draw this to scale. These beams are actually much deeper than this, but that means there's some tension transfer there, and there's but usually what ends up happening is a big crack forms right here, a big crack, big crack, big crack, huge crack. Can't see it because large crack forms right there, and it pretty much acts like a simply supported beam again. So I hear you. It's weird, it's challenging, it's strange to know on some of these structures on whether to make something a pin connection, whether to make something is truly continuous, whether to make something is somewhere in the middle. And in the end, I'm a big fan of just being conservative. That unless I know that I have load transfer, unless I designed it, I'm sure I know that everything is going to be great, then I pretty much always assume it's going to be a simply supported connection. And almost always. And there's videos about that in my steel notes where I talk about evaluating whether something is a fixed connection or a pin connection, and that may be valuable to you. So you may just want to go back and look at those and see what those are all about. So we are going to wrap the chat up right now. I'm going to say hi to a few more people here. Say, hey, thank you, Gian. I think it's Gian. Thank you so much. I really appreciate it. I'm really glad you like it. Thank you for the thumbs up. And David, man, thank you so much. Let's see how retrofit process. I'll tell you what. We'll talk about retrofit in the future, David, if you want, or maybe we can talk online if you want to. And let's see. Yeah. Let's see if there's anything else. Last question here. He wants to know can you tell me more about flow of stresses and how to figure that out? I think this is a great way to end. I think this is a very, very challenging topic on how to think about this. I think that this is all about what free body diagrams are about and what physics, when you take physics, you're supposed to learn some of this stuff in physics. And I think this is a skill it's a skill. It's not easy. And you have to envision structures, you have to look at structures, you have to think about how the loads transferred in an actual structure, and that's kind of what you have to do. It takes practice, and it helps to have people you can bounce ideas off of and that you can learn from. But it is invaluable. It is insanely important. And what I like to say is you become the force, right? You think about, where is the force going to go? Where is it going to flow? What is it all about? And that is how you figure out exactly where your loads are going to end up going. You can actually just kind of draw and ask yourself where the force is going to go. If you're stuck and you don't have any of those things, you could use a finite element program if you wanted to. You can make a big mesh, a big grid. You could start to put loads on it, and you can start to get a feel for how the loads move and how they flow. That's another tip that you could end up using. If you're doing a graduate degree, you can actually do loads, full scale structural loads. That has taught me a ton to see how structures actually fail and what they're all about. Actually study failures, study structural failures. And that's a big way too for you to learn how load flow works, load path works, but it is extremely powerful. And it is one of the secrets to becoming a great structural Jedi. So I think that's an appropriate way to finish in my Jedi Knight robes. And I thank you to everybody and everyone else. Hey, Ed, thanks from the Philippines. Thanks for saying hi. And hey, Lewis, thank you so much for all the encouragement, all the thought, all the help, man. I really appreciate it. And so, hey, please keep asking questions. Please keep being curious. Please keep pushing the limit, because we need you. The world needs you. The world needs people that are trying to be better and trying to provide value to the people around them. And I know that's who the people are that are on this call. So with that, I am going to push off. Take everybody. Toodles.